Hello and welcome to the lecture on 4.7. Today we're going to talk about logarithmic scales. Start with the definition. On a logarithmic scale, numbers are represented by their logarithms. Now, what this does is it allows us to view data in a more manageable way. Now, I'm going to list in metric tons the masses of many of the vehicles in the Star Wars universe. Now let's put this on a scale. If we put it on just a normal scale, let's say that we have our 0 point is here. And then here would be star killer base, which is 2.2425 times 10 to the 20th metric tons. If I wanted to list the rest of these vehicles in the Star Wars universe, they would all be about here. Star Killer Base is so much more massive than the rest of the vehicles that are listed here that all of them are within this region, this one little dot right here next to 0. If you don't believe me, then we can do 2.245 and you cut that in half. This would be about 1.12-ish, somewhere around there, times 10 to the 20th. If we cut this in half, then you're at roughly 5 times 10 to the 19th, and so on. As you can see, we're already here, and we're times 10 to the 19th, just barely times 10 to the 19th. The next most massive object is Death Star 2, and that's times 10 to the 15th. So we would have to go all the way down to around here in order to get to Death Star 2, let alone the rest of these, which are between the Death Star 2 and 0. So this is just not a feasible way to distribute our data. Instead, what we're going to do is use what we call a logarithmic scale. So on the logarithmic scale, we're going to list out all of these vehicles, but we're going to list the logarithm of their masses. And this is the logarithmic scale for the same exact vehicles in the Star Wars universe. Notice that the spread is a lot nicer. We have our Star Killer Base way out here. Our Death Star 2 is very massive compared to the rest of these, and it's a lot closer to Star Killer Base. Now, how we get these values, as I stated before, is we take the logarithm of each of their masses. So if we take the logarithm, log base 10, of the mass of Star Killer Base, we're going to get a little bit more than 20. And that's what we have here, 20.35. Similarly, if we take the logarithm of the Millennium Falcon, which is almost 1,000, almost identical to 1,000, then the logarithm base 10 would be roughly 3, which is exactly what we get, 3.00. Note, keep in mind the relationship between the data points on this graphic has changed. On this graphic, the relationship between a point A and A plus 1 is a factor of 10. Remember, in order to get these data points, we took the logarithm of the previous data that we had, log base 10 specifically. That means that the relationship between A plus 1 and A is that A plus 1 is 10 times bigger than A. The Constellar class at 4.04 is roughly 10 times more massive than the Millennium Falcon at 3.00. The Nebulon B frigate at 5.3 is roughly 100 times more massive than the Millennium Falcon at 3.00. Notice the relationship between numbers on this scale. As I stated before, we're moving up by factors of 10. So a number 5.03 is 100 times bigger than a number 3 because their difference is 2 and 10 to the second power is 100. The next topic I want to cover is the pH scale, which is a logarithmic scale. pH equals negative log of H plus, where H plus is the concentration of hydrogen ions measured in moles per liter. pH 7 is neutral. pH less than 7 is acidic. pH greater than 7 is called basic. Do an example here. The hydrogen concentration in Moncala oceans is on average 6.309 times 10 to the negative 9th. Find the pH. So what we do is we take our equation here. pH is equal to this logarithm. And we do pH is equal to negative log base 10 of H plus. Now, H plus stands for the hydrogen concentration. So if that's what we're given, the hydrogen concentration in Moncala oceans is on average this number is going to be H plus. And we're looking for what pH actually is, what the pH score. So we get pH is equal to negative log of 6.309 times 10 to the negative 9th. And we get that it's equal to 8.2, which is just very slightly basic. Try one. Acid rain falls in the industrial sector on Coruscant. If the pH is 3.5, find the hydrogen concentration in the rain. This problem is actually going to be sort of opposite of what we did here. Here, the hydrogen concentration is what you're given, and you're looking for pH. The problem that you are to do, you're given the pH is 3.5, and you're trying to figure out what the hydrogen concentration is. The next thing I want to talk about is the Richter scale. The magnitude m of an earthquake is m equals log of I divided by s, where I is the intensity of the earthquake measured by the amplitude of a seismograph taken 100 kilometers away from the epicenter of the earthquake. And s is the intensity of a standard earthquake, whose amplitude is 1 micron, or 10 to the negative 4 centimeters. Now, if you didn't know, the Richter scale measures how big our earthquakes are. The Richter scale tells us, uses the intensity of the earthquake from 100 kilometers away, measured by a seismograph, to give us a magnitude. The magnitude of a ground quake on Malastare is 7.4. Find the intensity. So here we're using a Richter scale on Malastare, so it's not called an earthquake, obviously. We just call it a groundquake in the Star Wars universe. But we use this, m is equal to log base 10 of I divided by s, to figure out what the intensity of the earthquake actually is. So here, remember that s is equal to 10 to the negative fourth. And m is the magnitude. Now we know what the magnitude is. It's given in the problem. The magnitude of the groundquake is 7.4. So our m is equal to 7.4. We do 7.4 is equal to log base I, which is the intensity, that's what we're looking for, divided by s, which is 10 to the negative 4. And then we solve for I. And that's it. So here, we would take both sides to be a power of 10 to eliminate this logarithm. So we get 10 to the 7.4 is equal to 10 to the logarithm of this, which is the same thing as I divided by 10 to the negative 4. And then we multiply both sides by 10 to the negative 4. So 10 to the 7.4 times 10 to the negative 4 is equal to I. And I is equal to 10 to the 3.4, which is roughly 2,511.886 cm. Right one? Suppose a quake on Naboo has an intensity of 4.25 centimeters. Find the magnitude of the quake. Now this is, again, the opposite of the example. Here, in this example, we're given the magnitude, 7.4, and we're looking for I. In the problem that you have, you're given the intensity, I, and you're looking for m. The next thing I want to talk about is the decibel scale. The decibel level B is measured B equals 10 times the logarithm of I divided by I sub 0, where I sub 0 is 10 to the negative 12th watts per meter squared, and it's a frequency that is barely audible. I is the intensity of the sound, also measured in watts per meter squared, and B is just measured in decibels. In decibels, just like the Richter scale and the pH scale, we know what something is down in the denominator of the logarithm. I sub 0 in this case is 10 to the negative 12th, which is known. You just plug that in whenever you're using this particular formula. Do an example. The Galactic Senate erupts into a shouting match of debate. Find the decibel level if the intensity was measured at 3.16 times 10 to the negative 4th watts per meters squared. So here, we're given intensity. We know what the intensity is. That would be I in our previous formula. So B will equal 10 times log base 10 of I, which is 3.16, times 10 to the negative 4th, divided by 10 to the negative 12th. So all we do is resolve this. I can move this 10 to the negative 12th in the numerator, and we end up with B is equal to 10 times log of 3.16 times 10 to the negative 4th times 10 to the 12th. This 10 to the 12th and 10 to the negative 4th will sort of cancel out a little bit, and we'll have 10 to the 8th left. This is going to be 10 log 3.16 times 10 to the 8th. And then we just take the logarithm of this number, and we end up with roughly 10 times 8.5, which is equal to 85. So the decibel level would be 85. Right. I don't have a try one problem for this, so this is going to be it. I will see you all in the next lecture.